All right, so sorry this section is already filled out. I've had 2 technical difficulties with the recording and I couldn't bear to erase this a second time with all the color. So let's read through it. So you might have noticed that we have local mins. Local mins look like this. And if we have a shape like that, then my function is concave up. And at local maximums, my function is concave down. So now the first derivative test works perfectly well for finding local mins and maxes, local extrema. The second derivative test is just an alternative test to do the same thing. It's truly a matter of style. Okay, so this is how the second derivative test goes. Suppose that your second derivative is continuous for all x values near k. If your first derivative is 0, so we've got a horizontal tangent to my function at x equals k, and my second derivative is positive. If my second derivative is positive, that looks like concave up. I like drawing a picture for myself, either literally draw it or draw it in my mind, because it feels very strange to say positive and then minimum. But if I say, if the second derivative is positive, my function is concave up, that feels very natural. And then I look at a picture of what concave up looks like and I say, oh yeah, concave up is in fact a minimum. Remember, maximums and minimums are y values. We have a minimum here at x equals k. The minimum is f of k. All right, if your first derivative is 0, got a little horizontal tangent here at x equals k, and my second derivative is negative, well then we have a local max. And again, saying negative and then max feels very, very strange. So what I like to do is go ahead and draw my little horizontal tangent. If the second derivative is negative, my function is concave down. Oh right, concave down looks like a maximum, right? And again, you can just draw it in your mind, but saying negative up and then max, or sorry, negative down and then max kind of feels a little strange. So I get a picture of concave down in my mind before I say, oh yeah, it's a max. Now, there is one bummer about the second derivative test, is that if your first derivative is 0 and your second derivative is also 0 at that x equals k, we don't know anything. It's inconclusive. F of k could be a max, it could be a min, it could be neither. We unfortunately then need your first derivative test, which is doing the increasing decreasing test and then interpreting the results. We need to do all that work to conclude whether or not you've got a local max, a local min, or neither at f of k. Okay, so now let's do example 6. I apologize if you hear some background noises of water. My upstairs neighbor sounds like they're taking a bath. COVID is crazy, guys. All right, here we go. So in example 1b, we found these critical points of x equals 3 and x equals 0. And then we went ahead and used the first derivative test to show that this function f has a local min at the critical point x equals 3, but didn't have any extrema at x equals 0. Let's glance at that real quick. All right, so here I'm back at the example 1. We went ahead and took our first derivative. We found out where it was 0, so these are the critical points that we're talking about, those critical values. And then we did the increasing decreasing test and interpreted the results. That's all the first derivative test is, really. It's doing the whole increasing decreasing test and then interpreting the results. Since the function is decreasing on either side of x equals 0, we didn't have a max or a min. However, since the function was changing from decreasing to increasing at x equals 3, we had decreasing to increasing, we had a local min. Now, this problem would have been done perhaps maybe simpler if we went ahead and used the second derivative test, at least for the one where there's the min. Okay, so let's go ahead and do that. Beautiful. Okay, so first we're gonna do the second derivative test to confirm that this function has a local minimum at x equals 3. So to do that, I need to do two things. I need to show that the first derivative is 0 there. I have a horizontal tangent, and then I have to figure out if the second derivative is either positive or negative there. Let's go ahead and do that. All right, so we already found the f prime of x, and I'm going to go ahead and write it in factored form because we did all this work already. So it's fairly intuitive to see that f prime of 3 here is 0. Right? Now, the second derivative, if f prime, now I actually want to look at it not factored for taking the derivative because I don't feel like doing product rule. Maybe I'll squeeze this in. Again, we did this work already. Right. So my second derivative is going to be 12x squared minus 24x. Because I know that my first derivative is 0 at 3, all I have to do is go find the second derivative at 3 and see if this is positive or negative. This happens to be 36, but I don't care about that. I care that it's positive. So what do we know? So we know f must be concave up at that value x equals 3. Concave up with that horizontal tangent means that we have a local min. Let's go ahead and write that. So since the first derivative is 0, and the second derivative is positive, you can write greater than 0 if you want. What must be true? F of 3 is a local minimum. Now, I don't know about you, but I feel like that is less work than doing the whole increasing and decreasing test and then interpreting the results. In other words, I think that this is a little bit less work than doing the full first derivative test. Now, the drawback to the second derivative test is when it's inconclusive. So let's look into that. So verify that the second derivative test is inconclusive at that critical point of x equals 0. So we know, let's get our colors matched. All right, so we already knew that the first derivative was 0 at 0 from the very first example. Right, these were our critical points, 3 and 0. But I'm just writing that note in. Now here's the bummer. The second derivative evaluated at 0 is 12 times 0 squared minus 24 times 0. Oh, bummer. 0 minus 0 is 0. This is sad. Second derivative test. Is inconclusive. We don't know anything. F of 0 could be a local max, a local min, or neither. And so if this were to happen to you, you would then have to go back and do the first derivative test. Let's scroll to that. All right, so you would have to see at x equals 0 right? That at that critical point on either side of it, the function is decreasing. So since the function isn't changing from decreasing to increasing or increasing to decreasing, there's no change there. We do not have a local min or max. So that would kind of be a bummer to start the second derivative test there, realize it's inconclusive, and then go ahead and do the first derivative test. Okay, so let's move on. All right, so our think pair share to conclude. So in example 3b, we used the first derivative to show that g had a local max at x equals 2 and a local min at x equals 2. I want us to go ahead and use the second derivative test to confirm these results. And I think I'm going to do this one with you. So the first step is to find where the first derivative is 0. And again, where means where in the domain. And we're using g here. Right, and we did this already. Here's your g prime is 3x squared minus 12. It's equal to 0. At 2 and minus 2 from both these. Oops, I said minus 2, so I wrote it. At x equals 2 and x equals minus 2. Now we don't have, you could, if you were doing the first derivative test, we would then do a sign test on the first derivative. This breaks up the interval of the domain for f prime into places where it could either be positive or negative. Instead of doing all that, we're just going to plug in these critical points into the second derivative and say whether or not the second derivative is positive or negative, right? So step 2, determine if the second derivative is positive or negative at these critical points. All right, so we need the second derivative, g double prime, right? Here's g prime. I'm going to take the second derivative. 3 times 2 is 6x. I'm going to just evaluate the second derivative at minus 2 and at 2. So the second derivative at minus 2 is minus 12. I don't care about the 12 part. I care about that it's negative. So since this is negative, what must be true? Then your g function must be what? Concave down. Okay, g looks like this. Concave down, that is a local maximum, right? So therefore, g of minus 2, and let's go do gray. And you can go find that function value on g, but let's just leave it like that. This is a local max. Yes, it feels weird to say negative and then max, which is why I like to put in this intermediate step. If the second derivative is negative, that original function is concave down, and then go, oh yeah, concave down looks like a max. All right, and we did this before. Let's glance back at that and see that we got the same results. All right, so here we are in example 3. G of minus 2, which is 18, we said is a local max. Check. All right, so now we found what the second derivative was, if it was positive or negative. In this case, negative at one of the critical points. X is minus 2. Now let's do it for the other one. X is 2. The second derivative evaluated at positive 2 happens to be 12, but what I care about that is that it's positive 12. So what must be true? My original function g must be concave up. My second derivative is positive, so my original function is concave up, and concave up looks like what? It looks like a max. So therefore, g of 2 is a local maximum. Let's go back to example 3 and confirm that that's what we got before, and that'll conclude this video. I'm really glad that I just said that because your teacher is super dyslexic. I'm not redoing this video. Positive, concave up, that's all correct, and then I keep saying that the picture helps me. What did I draw a picture of? I drew a picture of concave down. You can laugh at me. Beautiful, right? And I wanted to draw a picture of concave up, and concave up, what does concave up look like? It looks like a minimum, right? So when I say positive and up, that's comfortable for me. And if I draw my picture right and then look at the picture and say minimum, I'm happy. Let's go look at example 3 and see that this confirms the results. All right, here we are. Okay, so in example 3, we said that g of 2, which happened to be minus 14, was a local min. And we did that by doing the first derivative test, which is really just doing the increasing and decreasing test and then interpreting the results.